Okay, good morning, everyone. I am Mary Salvania from King Abdullah University of Science and Technology, and I am here to present our work on parallel space-time likelihood optimization for air pollution prediction in large-scale systems. Here we have a movie showing an hourly sequence of spatial images of logarithmic transform particulate matter concentrations from the NASA website over Saudi Arabia and Midwest United States. Particulate matter are solid particles or liquid droplets that remain suspended in the atmosphere. The plots exhibit some spatial patterns, such that the measurement at any location is similar to some degree to its neighbors. Particulate matter also has significant temporal characteristics. As we move forward in time, we can observe some general movement from north to south. And the values at each time point are also related to some degree to the values at the previous time points. For space-time processes such as this, often we want to make scientific inferences and forecast future concentration levels. One approach to accomplishing such goals is to use computational physical models, such as pollutant dispersion models. Those models, however, require many assumed inputs, including physical parameters, boundary conditions that non-expert users may find very hard to supply. An alternative approach is to use data-driven models. One of them is the class of space-time geostatistics models. Those models are complement to physics-based modeling, and they are suitable for geographically referenced data. They aim to understand the dependence across space and time and across different types of data by seeking correlations, and they are adequate for many space-time phenomena. There are challenges, however, to space-time geostatistics modeling. These are the cubic growth of computational complexity and the quadratic increase of storage complexity with the number of space-time locations. This is because the methodology involves an iterative procedure that requires Cholesky factorization at each iteration. In this presentation, I will show how these problems are addressable through multi-level parallelism using asynchronous execution of computational tasks. The rest of the presentation will follow this flow. I will continue with some preliminaries where I will give a review of the concepts related to space-time geostatistics, the model that we will use, and how we can make predictions using that model. I will also discuss the ingredients we will need for high-performance implementation. Next part, I will outline the main contributions of this work. Then I will present our proposed two-level parallelization framework. I will then discuss how we assess the performance of our implementation using synthetic and real space-time datasets, and then give a summary and point out other avenues for future research. Let's start with a review. So here is the setup of our space-time geostatistics model. Suppose we have a vector of measurement Z1 from N1 sampled space-time locations, where each component of Z1 is a measurement at the sampled space-time location. Suppose we have another vector of measurements, but those are missing measurements at N2 unsampled space-time locations, and we want to predict those measurements. Our modeling framework requires that Z1 and Z2 be jointly Gaussian, meaning we can write it in this form, where we have mean vectors mu1 and mu2 of Z1 and Z2, and covariance matrices sigma 1, sigma 2. Sigma 1, 2 is the cross-covariance matrix of Z1 and Z2. Prediction for Z2 can be performed using the concept of conditional distribution of Gaussian processes. This means that the best prediction for the missing measurements Z2, which we denote Z2 hat, can be found using this formula. From the formula, we can see that prediction relies on the mean vectors and covariance matrices. So it's important that we supply the correct mean vectors and covariance matrices so that we can get accurate predictions. In practice, mean vectors and covariance matrices are estimated from the given measurements Z1. This is done by choosing and fitting a parametric mean function and a parametric covariance function to the data. In this work, we will suppose that the mean vectors are zero vector, so that we only have to deal with the covariance matrices. To model the covariance matrices, we need a parametric spacetime covariance function, which we denote C with arguments S1, S2, T1, T2, and it's parameterized by this theta vector. So the covariance function propagates the entries of the covariance matrices, and it describes the strength of dependence of the measurements at any two spacetime locations. Generally, we expect that when the locations are near to each other, the covariance is higher compared to that of two locations that are far from each other. There are many choices for the covariance function. One of the most popular choice is this Knighting covariance function, which has the form. Here we can find a separation vector in space, the H, and the temporal separation, the U. This model has 6 parameters: a variance parameter, a smoothness parameters in time and space, and range parameters in space and time, and also a space-time interaction parameter. When beta is equal to 0, we call the model separable, and it implies that the dependent structure in space is independent from the dependent structure in time. Non-zero values of beta imply that there is interaction between the dependent structures in space and time. We will simulate from this model, and we will see how the space-time measurements change as we move through time. Here we have two simulated space-time fields from the non-separable and separable versions of the model. The two models have the same parameter values except for beta. From the figure, we can see that the fields are identical at time equals 1. However, they evolve in different ways through time. The non-separable model is more flexible as it takes a separable model as a special case. The unknown parameters of the spacetime covariance function can be estimated by maximizing this Gaussian log likelihood function. And this is where the grand challenge lies in Gaussian geostatistical modeling. It is in the inversion of sigma, as this requires Cholesky factorization, which is extremely demanding in terms of memory footprint and computation. And this is where statisticians are rendered helpless when they encounter sigma with a very huge size, as it's virtually impossible to perform the inversion with most of the statistical software that they are using. A C-based software called ExaGeoStat was developed for high-performance computing on many core systems that uses tile-based linear algebra algorithms to parallelize the core operations done on the Gaussian log likelihood function. ExaGeoStat depends on various software libraries. The maximum likelihood optimization is performed using the NLOPT optimization library. The underlying linear algebra matrix operations are done by Chameleon and Hikma. These are tile-based high-performance linear algebra libraries that rely on task parallel programming models instead of the less efficient block-based algorithms. The Hikma library is the hierarchical approximation version of the Chameleon dense library. The dynamic runtime system then deploys a task across different hardware resources. Chameleon improved the traditional bulk synchronous programming of LAPACK. The default paradigm behind LAPACK is block column algorithms. The tile-based algorithms, on the other hand, split the matrix into small tiles instead of tall panels. The numerical algorithm behind Chameleon is translated into a directed acyclical graph, or the DAG, where the nodes represent the task and the edges represent data dependencies. And the runtime system can be used to schedule the DAG task across different hardware resources. This is an example of a DAG to perform Cholesky factorization of 4x4 matrix. Finding the maximum value of the log likelihood function requires several optimization iterations over a pool of candidate solutions. Further scalability can be achieved by parallelizing this optimization process. One way to do this is using particle swarm optimization algorithm. PSO algorithm starts with a group of randomly generated potential solutions called particles, and each particle is associated with a velocity vector that directs the next step of the particle. And at each iteration, every particle would search around for the solution. The PSO algorithm is conceptually simple and compatible with parallelization. Later on, we will see how we incorporated the PSO algorithm into ExaGeoStat. Our contributions are the following: implementation of high-performance spacetime model on large-scale systems, visualization of spacetime random fields generated by the high-performance implementation, incorporation of the PSO algorithm to the Emily operation to utilize the execution performance on distributed environments, illustration of benefits of flexible versus simple spacetime model via large-scale spacetime experiments, and application to air pollution datasets from the Middle East and the US. The proposed two-level parallelization framework. For our parallel optimization strategy, we need an MPI default communicator, the MPI split function, the MPI com split function, and the PP swarm algorithm, which is a parallel implementation of the PSO algorithm. In a nutshell, we split the default communicator into a set of sub-communicators where each can be used to evaluate a single log likelihood function solution. Here is a depiction of our proposed framework. Assuming we have a set of 32 nodes, the MPI com split function can be used to split the default MPI com world communicator into 8 sub-communicators. And each sub-communicator includes the nodes that will internally communicate to evaluate a single MLE solution with the aid of the underlying parallel linear algebra library and the dynamic runtime system. In this way, we can evaluate several log likelihood functions in parallel while keeping the MLE operations low-level parallelization. We will assess the performance of this framework. To do so, we generate synthetic data sets with different spatial and temporal dependence profiles that illustrate various cases that can appear in real data. We also obtain 2 real particulate matter data sets, each with more than 400,000 spacetime locations, to demonstrate and validate the prediction accuracy of our implementation. The performance is tested in an Intel-based Cray XC40 system with more than 6,000 compute nodes, and all experiments were conducted on the whole number of cores with different nodes. First, we show the advantage of using non-separable over separable model. Generally, statisticians, for practicality, would prefer a model with less number of parameters. In this case, the separable model, since it will take less time to find a solution. In this experiment, we show that if we go for a separable model, when the actual model is a non-separable one, then we actually lose some accuracy. We simulate synthetic data sets with different beta values and fit both the separable and the non-separable model on the training set, which is 90% of the whole data set, and perform predictions on the testing set, which is the remaining 10%. We do this for 100 rounds, and we plot the resulting prediction errors. From the results, we can see that both models are at par in accuracy when the interaction in spacetime is weak, which is beta equals 0.1. And the difference between the two models appear when tested in moderate and strong interaction scenarios. And as expected, the separable model cannot adequately capture non-negligible spacetime interaction. Since the non-separable model is preferable due to its flexibility and accuracy, we check whether the parallel implementation can recover all the parameters of the model. Here we have the values of the parameter estimates for every dependent scenario: weak, moderate, strong in space and time. The median values of the parameter estimates match the true parameter values, which are highlighted in red. This shows that our implementation can satisfactorily perform in any combination of space-time dependence. We move on to the real data. The first real data set, these are the log particulate matter in Saudi Arabia. We expect, so this is the one for Saudi Arabia. We expect some strong correlation in space, as there are recognizable spots of yellow, red, and blue, indicating that the measurement is similar to its neighbors everywhere. We may also expect a weak correlation in time, as the spatial images are substantially different from one point to the next. The second data set is this one from the Midwest US, where we have moderate to strong correlation in space also. However, unlike the first data set, we can expect strong correlation in time because, as we can see, the spatial image structure from the first hour tend to persist even until 20 hours. Here we have a summary of the estimated parameters of the two models and the prediction errors and uncertainty. We prepared two testing data sets. Testing dataset 1 consists of random missing observations inside the time frame that we consider. Testing dataset 2 consists of all the missing values on the map for 2 time points ahead. The parameter estimates imply several properties regarding the particulate matter. One thing we should notice is that the non-separability parameter beta is larger in Saudi Arabia than in the US. This means that we have a stronger space-time interaction of particulate matter in Saudi Arabia. The MSP values show that the separable model returns higher prediction errors than the non-separable model. The difference may not be that huge because the values we are modeling are very small. So to further show that the non-separable model is superior, we perform a pseudo cross-validation study wherein we take a subset of the testing data sets and repeat what we just did for 100 rounds and compute the resulting MSPs. Here we have the box plots of the prediction errors, which show that indeed the non-separable model returns lower errors in both weak correlation and strong correlation cases. These real data results mirror what we saw in the synthetic data experiments. We have here the performance of a single MLE optimization step using different number of nodes on Shaheen 2 supercomputer. Each bar represents a specific workload distribution, where the first number represents the number of MPI sub-communicators, and the second number represents the number of nodes in each sub-communicator. We evaluate these combinations for a given set of nodes using different matrix sizes. From the plots, we can see that the best performance improvement of use can be obtained using the smallest number of nodes per sub-communicator that can handle a given problem size. In figure A, for example, with 128 nodes, the performance improvement of using 8 MPI subcommunicators compared to a single communicator with all 128 nodes is about 6x with a problem size of 40,000. However, in the case of 160,000 locations, we only have 2 times performance improvement from the implementation. In figure C, for another example, in 512 nodes, the achievement we have is 25 times and 11 times with 40,000 and 160,000 locations. Our proposed framework shows higher performance improvements with more nodes. For instance, if you look at 160,000 problem size, the achieved performance are 2x, 4x, 11x, and 23x using 128, 256, 512, and 1024 nodes. Here we have the performance gain applying the two-level parallel Emily implementation compared to the one-level parallel implementation. We use 6 different matrix sizes for the evaluation. In figure A, we report the one-level implementation performance where only the parallel linear solvers are applied to the log likelihood function. The empty red box show the peak performance that a certain number of nodes can theoretically achieve. What we see here is that with smaller workloads, the performance degrades with a large number of nodes when there is not enough work to keep all the nodes busy. From figure B, we can see the performance using the two-level parallelization which we propose. And the figure confirms the scalability of our implementation with a different number of nodes. Compared to figure A, our proposed implementation satisfies stable performance with different number of nodes and with different problem sizes. Here we show the boost in performance in using the two-level parallelization compared to one level using 1024 nodes on Shaheen 2 supercomputer. The figure shows that the proposed framework can achieve 3x more than the baseline framework using a 490,000 problem size. Here we show the time to solution where the number of optimization iterations is fixed to 100. When one level parallelism is used, like in figure A, smaller workloads take the same execution time even when we increase the number of nodes. So at a certain point, increasing the number of nodes will not improve the time to solution anymore. For instance, going from 256 nodes to 512 nodes will not accelerate the execution time. The proposed implementation, on the other hand, in figure B, keeps the execution time speed up gains with more nodes. We can see that going from 512 nodes to 1024 nodes, the time to solution decreases. The figure here also summarizes the achieves speed up by one level and two level parallel implementations when we double the number of nodes. As shown, the proposed two level parallel implementation always achieves speed up close to the theoretical speed up. To summarize, we proposed a two level parallelization framework of a geostatistical spacetime model. At the upper level, we have MPI sub-communicators performing independent log likelihood function evaluation with different sets of parameters via the parallel PSO algorithm. At the inner level, we have task-based parallel technique to perform linear solver operations on a given set of nodes, representing a single MPI sub-communicator. We demonstrated through synthetic and real data sets the merits of the proposed implementation. We have achieved high prediction accuracy with up to 757 TFLOPS using 1024 nodes in the Kaust Shaheen 2 supercomputer. That's around 63% of the theoretical peak. Other avenues for further research will be to use stylo-rank and mixed precision approximations to accelerate further the modeling process. Here are the resources that we use, the references. And I am ready for your questions.